moving on to question number 9. A 70 kilogram person is standing in an elevator. We need to draw a free body diagram and determine the normal force acting on the person if the elevator is at rest, the elevator is moving up at 2 meters per second. Notice the units. The elevator is moving down at 2 meters per second. The elevator is accelerating upward, keyword, 2 meters per second squared. The elevator is accelerating downward at a rate of 2 meters per second squared. The relationship between the normal force and the force of gravity can vary if there is acceleration happening in the y-axis, which is why the question has been asked the way that it has been asked. So what we're going to do is we're going to derive a general equation to figure out what the value for the normal force is going to be in terms of the mass of the individual and the motion of the elevator, which has been outlined in parts A through E. Focusing on the givens, we know that the mass of the individual is 70 kilograms. In part A, the elevator is at rest, so therefore V equals 0 meters per second. In part B, it said it was moving down at 2 meters per second. The units indicate that that means it's a speed/velocity. Had to do a little quick edit on my given list here. I missed one of the parts. So in part B, we're moving up at a constant speed of 2 meters per second. In part C, it's moving down at a constant speed of 2 meters per second. We know that it's speed because of the units, meters per second. That implies that it was moving with constant motion. Then in part D, it specifically says that it was accelerating up at 2 meters per second squared, and in part E, down at 2 meters per second squared. Conceptually, in parts A, B, and C, rest, positive constant motion, negative constant motion, the acceleration in all three of these cases is going to be 0 meters per second squared. And again, we're trying to find the normal force, capital N, Mr. LaRusso. So let's start off with our free body diagram. So we're just going to do a generic free body diagram and equation. So we know that the normal force is acting up and the force of gravity is acting down. But the way that I have these vectors set up is this implies that the acceleration is 0 meters per second squared, because the way that I drew the magnitudes of the normal and gravity is equal and opposite. However, if the elevator is accelerating upward, this means that the up forces have to be stronger than the down forces. The force of gravity does not change because the force of gravity is entirely based on the mass of our passenger in the elevator. So in order for this to occur, as the elevator starts to accelerate up, the floor is pushing upward on our passenger, which means that the normal force is going to have a slight increase. This is why you get the sensation that you feel a little heavier in the knees when you first get into an elevator. Now, when it goes back to equal, the acceleration would be 0 meters per second squared. However, if the elevator needs to accelerate down, and that's one of two ways that can happen, i.e., as the elevator was moving up, it slows down to come to a stop at the floor, or the elevator is, you get on the elevator and then you're going down towards the lobby. In both cases, if the acceleration is down, this means that the down forces have to beat the up forces. And again, Fg can't change because that's based on the mass of the individual. So in this case, the normal force would have to shrink slightly. And this is where you get that sensation of feeling a little bit lighter. People often will jump at the end of the elevator ride so they can get that extra height. And that has to do with the fact that when the elevator is slowing down, experiencing negative acceleration, the normal force is a little less, and you can get what appears to be a little bit more height when you jump. That's not recommended that you do that. That's an easy way to get stuck in the elevator for a couple of hours. Okay, so let's get this back in the original configuration. So what we're going to do is we're going to generate an expression for Fn entirely algebraically. So we've got the net force is equal to Fn plus Fg. There's only forces in the y component, so we don't have to worry about x and y here. There's just only one component that we're worried about. Next, I get rid of the vector notation and I replace Fnet with MA, Fn with positive Fn, and Fg with a negative. Okay, so I really need to clarify something here. This is very important. I definitely made a decision about the direction of the normal force because it's always going to be positive in this case. Gravity is always going to be negative. But here's the thing about Fnet. Fnet can either be positive, negative, or zero. there are three possibilities for the net force. It's either going to be a positive number, a negative number, or zero. So we are trying to make a general equation. So I can't decide and say that this is going to be positive. I can't make this negative, and I can't just say this is equal to zero. So what I do is I make no decision in terms of its direction, and I let the acceleration take care of that. So this side of the equation will either become positive, negative, or zero based on whatever value we have for our acceleration. So if our acceleration is positive, then the net force will be positive. If the acceleration is negative, the net force will be negative. And if the acceleration is zero, well, anything times zero is zero. And that's why we write it the way that we do. Next, we're going to isolate for our term of concern. Sorry, I usually highlight in green when I'm doing the terms. Fn is our term of concern. Fg, we're going to need to bring to the other side. And since it's subtraction, the opposite of subtraction is addition. So we get Fn is equal to Ma plus our Fg. Flipping the equation around, we get Fn is equal to Ma plus Fg. But we know that Fg is equal to mg. So we can replace our Fg with mg. And notice this, we got a common factor of mass in both terms. So I'm going to factor that out and common factor it out, of course. That gives me mass times bracket A plus G. I'm going to call this my equation 1. And this is our general formula that will give us our value for our normal force, all dependent on what the value for A is going to be. Now, remember, G is always just 9.8. It's not positive or negative. It's just 9.8. And a reminder as why that is, we already made it negative here. That's the direction there. So the Fg term is just a magnitude. All right, so let's take a look at all these examples. So for part A, it's at rest, therefore the acceleration is zero. Substituting in zero in for A, we get a normal force of 686.0 newtons. In part B, and I realized oh dear, let's fix that. I realized I forgot the actual part B. No problem. We're going to do a little copy and paste here. And boom, the magic of editing. So part B, we're moving up at a constant speed of 2 meters per second, or constant velocity of 2 meters per second, which means our acceleration is 0 meters per second squared. And as you can see, we get the exact same normal force. So if we're at rest or moving up at a constant speed, the normal force feels exactly the same. Therefore, it should be of no surprise that when we're moving down at a constant speed and still have an acceleration of 0 meters per second squared, the normal force is exactly the same. The only time we feel a difference is when the elevator is experiencing acceleration. And that's with part D and part E. When the elevator is accelerating up at 2 meters per second squared, that means that the normal force has to be stronger than the force of gravity. Substituting in positive 2 for my acceleration, I get 826.0 newtons. That little extra force is what causes us to accelerate up. And that's what makes us feel a little heavier in the knees. Then when the acceleration is negative, the normal force has to be smaller than the force of gravity because the force of gravity has to win that fight. And it makes sense that when we substitute that in, we get a total of 546.0 newtons, which makes us feel a little bit lighter in the knees. Once again, in summary, when the acceleration is 0, normal and gravity are equal and opposite. When the acceleration is positive, Fn has to be greater than Fg. If the acceleration is negative, Fn has to be less than Fg.